In section 24.4, we have only a couple different ideas that we need to introduce here. But to get to those, we need to look at some particular notations. Our multiplication rule. If an experiment involves k components, which the possible outcomes are n1, n2, n3, all the way to nk, then the total number of experiment outcomes is equal to n1 times n2 times n3 times nk. And because we're going to be multiplying many things together, we end up needing to go back to something that you probably saw in high school, but it might have been a while. So I'll remind you what a factorial is. When we want to convey m factorial, it's m times m minus 1 times n minus 2, and we'll keep progressing as we multiply additional terms until we get down to 1. So that's the notation. M factorial is that the product of all those terms. Now we're ready to calculate some ideas in 24.4. In 24.4, we're going to be looking at permutations, combinations, and binomial coefficients. Binomial coefficients are something that we use in mostly in chapter 24, but I think they come up in 25 as well. The binomial coefficient might be written as the, in parentheses, a stacked on b. That's not how you'd say it. You just you depict it with that presentation and then calculate it with a times a minus 1 times a minus 2 all the way down to a minus k plus 1, then divide that by k factorial. And that's just called a binomial coefficient. And we've just developed the shorthand that it can be written as the parentheses a stacked above k. And you will again have this equation available in the equation sheet. Permutations. The number of different permutations of n different objects taken in order k at a time, where n is greater than k, is described as this term p of n over k, so that tells you its permutations, is n times n minus 1 times n minus 2 all the way down to n minus k plus 1. And that can be calculated as n factorial over n minus k factorial. And without repetitions, this is n to the kth power. An example of a problem involving permutations in this formula is, in how many ways can first, second, and third come out in a 10-horse race? So in this case of first, second, or third, order matters. So we're going to be taking 3 horses at a time out of 10 possible horses. So n is 10 and k is 3, and we simply use the formula above and get 10 factorial over 10 minus 3 factorial, which is just equal to 10 times 9 times 8, or 720. So there are 720 permutations of the number of ways that first, second, and third can come out in a 10-horse race. Next, we're going to look at combinations. A combination of k objects from n objects, where k is smaller than n, is in an unordered sequence of k objects selected without replacements from the n objects. So we've got a big group of n, and we're going to pick out k of those objects. The number of possible combinations of those k objects from those n is written as c with the superscript n and the subscript k, is written with the binomial coefficient n upon k, and that is calculated as n factorial over n minus k factorial times k factorial. If we look at a particular example of these combinations, we might be looking at how many different random samples of size 3 can be obtained from a population of 50. If we apply the formula in this case, we would get n is 50 and k is 3, so it's 50 factorial over n minus 3 factorial times 3 factorial, and it's 50 times 49 times 48 in the numerator, and 3 times 2 times 1 in the denominator. If you're wondering why we don't have 47, 46, 45, etc. in the numerator, it's because we similarly had a 47 times 46 times 45 in the denominator, and those canceled each other out so that we end up with an answer in this case of 29,600.